Good afternoon. So we will start today solving problems on chapter 8. So this chapter is mainly an application of the energy equation, of the generalized energy equation. Okay? So if you remember in chapter 5, we had at the end an energy part. This will be like, if you want, it's included in this chapter, and here it's more developed because we consider losses, also possible losses. When we applied before the energy equation, let's say, we didn't take into account maybe losses, okay, because we just considered that, or losses were given sometimes, or we say that maybe losses are neglected and we solved before. So here it's a little bit more complex because we have to account for minor losses and major losses, and we will see how to do it. Okay. So to start with, I will start with some examples of the book because they will help you in uh, catching the method to use for different types of problems. So we'll do different types of problems because sometimes, for example, we have the diameter that is not given, sometimes the velocity is not given. So this will vary between one problem and the other. Okay. Now, to start with, you just watched 1 hour, but I told you try to watch more. Anyway, it's not a problem. I will explain it for you. It's not complex. Okay, it's very simple. So I will, in each step, I will explain what is the equation. Okay, and then I will tell you what to use. Okay, so even the remaining part of the chapter is not very hard, so I can introduce it while doing the problem. Okay, because it's a little bit difficult to just have problems on only the first hour because they combine, in general, they combine minor losses and major losses in problems. Okay, so let us start by the first example and we'll see how to solve it. Okay, so we have air at temperature of 100 Fahrenheit and standard pressure flows from a clothes dryer. According to the appliance manufacturer, the 4-inch diameter galvanized iron vent of the clothes dryer is not to contain more than 20 feet of pipe and 490 degrees elbows. Find under these conditions the airflow rate if the pressure at the start of the vent pipe directly downstream of the dryer fan is 0. 0.2 inch of water. Okay, so here what we have a system that is operating. They gave us the initial condition. So we have that at the inlet. Okay, they gave us, we have the temperature condition. Okay, and we have that we are working at standard pressure flow. And then at the outlet, they gave us what is the exit pressure. They gave us, if you want here as the height, if they give you a height, the pressure will be rho g times this height. So since 0. 0.2 inch of water, I multiply the height given by gamma of water, I get the corresponding pressure. Okay? So I have, when they say just standard pressure, so you take the atmospherical pressure. Okay, so this is why we have P2, because when at the exit conditions, it's standard pressure condition, so it's the atmospherical value, and the inlet pressure is given to be 0. 0.2 inch of water, so we can calculate. Okay, so we have P1 and P2. Now, when they don't mention anything, okay, in general, they should be very accurate in the given. So they can tell you we are working at horizontal level, or they can tell you that no variation in elevation. In this case, you take that Z1 is equal to Z2. Okay, and now, yes, we can show a drawing. Yes. Okay. Here, the drawing is simple because look, you have a system. Whatever is the system, you don't care for it. So you have, let's say, they are saying that you have a length of 20 feet and 4 elbows of 90 degrees. So you can have it like this way, for example. I will show it. So if I want to draw it like, let's consider, for example, here, you have a first elbow of 90 degrees. This is now a second elbow. This is a, so for example, like this, okay? So you have a piping, just it's a piping system, okay, duct system. of total length. So total length is 20 feet. Okay, so this is the total length. So if you do the summation of lengths of each segment, you get 20 feet. And it contains 4 elbows from the initial point to the final point, and each elbow is is of angle of 90 degrees. Okay, so if you want here, you have inlet condition from here, and let's say the outlet from condition is from here. Since they didn't specify anything about the elevation, you can consider that the change in elevation is negligible. Okay, هلا they should tell you and neglect the change in elevation, for example. Or you can have your system in a horizontal plane. So if this system is in a horizontal plane, then no variation in elevation. Okay, so the initial conditions are given. I have P1. P1 is given to be corresponding to 0.2 inch of water. So all I have to do is to do gamma water times the height. Just please pay attention for units, okay? So when you work in English units, you should use feet, because gamma is given in lb per feet cube. So pay attention to convert the height of water into feet. So you divide. You know that 1 feet corresponds to 12 inch, so you should divide this value by 12 to get the value in feet. Okay, and from here you can determine what is the value of P1. Now for P2, it's since we are working in standard pressure, so we consider that at the exit it's atmospherical pressure. Okay, and if we are reasoning in gauge pressure, it's 0. Also here they should tell you, and this is gauge pressure. All of this information will be clear in the given in the exam. So now what I will do, I will write the energy equation from the inlet to the outlet. So what will happen when going from inlet to outlet? You are familiar with this part, okay? If you remember, so when you have no losses, this was your equation, okay? Conservation of energy. So P1 over gamma plus V1 square over 2G plus Z1 equals to P2 over gamma plus V2 square over 2G plus Z2. But here, losses are not negligible, so we should account for losses, okay? The losses are accounted through these two terms. So you have in any system, you have two types of losses. We say major and minor, okay? This term here is the major losses. And what we mean by major losses, this is due to the length of your ducting system, okay? And why they say they are major, because in general, any system, okay, due to the length, will have losses induced. And these losses will be in general dominant over minor losses, especially if you have very long piping system, okay? So, so when L over D is very high, when L, the length of the ducting system over the diameter, is large, okay, we can say that major losses will be dominant over a minor one, okay? Major losses will be dominant. Major losses. So sometimes in the given they tell you neglect minor losses. So you only account for the major losses, and this is because, and when they say for you that, this means that L over D is very large. Okay, so major losses become dominant. Now in other cases, when they don't tell you that you can neglect minor losses, you should account for all accessories in your system that can lead to losses. So if you have an elbow, if you have a valve, if you have a certain bending angle, anything, any fitting will induce minor losses, okay? And I will show you a table. You have a table for different types of accessories that will give you minor losses, and for each accessory, they will give you the corresponding coefficient loss Km, okay? So here, the other term here represents minor losses. So this is for minor losses, okay? And we will see here how we can find the value of minor losses and major losses in this problem. Five elbows. Look, 1, 2, 3. Yes, it's right. So no need for this part. Yes, 1, 2, 3, 4. Yes, no need for this part here. So the scheme I did is 5 elbows, not 4. Okay. So if the problem is saying 4, then you can stop this part. You can cancel it. Okay, because here you have, this is the first one. So this is first elbow. 1, 2, 3, and 4. Okay. So if the problem was 5, then we can add a part here. Now, in order to know what is the coefficient of loss for an elbow of 90 degrees, I should go to tables. So in general, they give me tables, they give me figures to find my coefficient loss. So let me give you, I will go to the table which will give you the value of KL. In general, in the exam, or we give you figures, or you can use, you will see that some figures will be repeated during the examples, and all are present in the book. So you can go to the book and you can see all these figures. Okay. So for example, you have a table. The table 8.2 of the book will give you the coefficient loss, minor coefficient loss for different accessory stuff. Okay. So for example, here, even for elbows, you have several possibilities. They can be, you can have a different angle. So they can be 90 degrees, they can be 45 degrees, and you have several options, flanged or threaded. So all of these will affect the coefficient of loss. So here in this problem, it's regular 90 degrees. They didn't say, we have flanged elbows. So it's regular 90 degrees elbow. So if you go to the table, you can select that KL for this type of accessories is 1.5. And as you can see here, this table will present for you the coefficient of loss for variable fitting. Okay, so you can have T's. Okay, you can have return bands like this. You can have, for example, valves. Okay, so depending on the, here they didn't give a figure, they gave the name. Sometimes they will give you the figure. So from the figure you can know what is the type of accessories involved. Okay, so here we have several possible accessories, and for each accessory we give the corresponding coefficient loss. So it's very simple. All you have to do, you go to your given, you see what is the name of the accessory. So here they said that we have 90 degrees elbows. Okay, so we selected the corresponding value for KL. Okay, now to continue, so KL, we are done with KL, we know it. Okay, now what we will do with this term, F times L over D. First, L is given, it's 20 feet. Okay, and the diameter also is given, so it's 4-inch diameter. So D is given, L is given, but the factor F is not given. Okay, so F is unknown. And we will see together how we can determine the corresponding value of F. Okay, so now what I will do, I will replace KL by its value. I will replace L and D by their values. I will replace P1 and P2. Okay, and for V1 and V2, why they will be equal? Because look, here you have a flow in a duct, and the diameter of the duct is not varying. So even if you have elbows and if you have the diameter for each cross section is the same. So since you have same D, so since we have same D, and assuming incompressible flow, okay, incompressible flow, then we can say that the volumetric flow rate Q is constant and Q is V times A. Okay, and since the cross-sectional area is constant, okay, so Q is constant and A constant, so V will not change. So V is the same. Okay, this is why here we have that V1 is equal to V2 and equal to the velocity inside my duct, equals to V at any place, okay, of my duct. Yes, in general, what is V1 and V2? Okay, in general, V1 is the inlet velocity, V2 is the exit velocity, and this V is the average velocity through my uh, system. But here V1 is equal to V2, so V average, okay, is equal to V1 and V2. Okay, so this represents when you calculate losses, it is average velocity. But here all will be equal, V1 and V2 and okay. So now what I will do when I replace into my equation, I will get a first equation relating F and V. Okay, so this is equation for me, this is equation number 1. But this equation for me is not enough. Why? Because it includes 2 unknowns and I have only 1 equation. Okay, so what I should do, I should write other equations relating F and V. Okay, now this can be done using the Moody chart, because the Moody chart is a chart giving relation between F and V. And let me show you the Moody chart. So if you want, the Moody chart is an example of the result of dimensionless analysis. You remember in the previous chapter, we said that when we want to do experiments, we should determine groups. And once we determine the number of groups, we can perform experimentation in order to vary, to know which parameter to vary. Okay. So here, for example, for piping systems, what are the main variables involved in piping systems? You have rho, the density of the fluid, because whenever we said you have a fluid in general, the most important characteristics are rho, mu, and velocity. So these are important characteristics. Plus here, since we have roughness of the pipe, so here my pipes are rough. We don't have smooth pipes. This is why a new parameter is included, which is epsilon. It represents the roughness of my pipe. So epsilon is another parameter, okay? And the friction losses F, okay, which are induced by due to if you want losses when I go over a certain piping system, I will lose energy. So another parameter is F related to major losses. So here you have 5 parameters, and if you do the analysis, if you do your analysis, since F is without units, so it constitutes a group by itself. F is a group by itself. Epsilon, the unit of epsilon roughness is length, so another group will be epsilon over d, and the third group will be the Reynolds number. So here in this example, you have 3 groups. Epsilon over d is group 1, Reynolds is group 2, and the friction factor F is group 3. And experimentally, what they did, they varied. For example, you can fix, let's say, 2 parameters and vary the other. And at the end, when doing for several experiments, you can come up with a curve, with several curves. Okay, these curves, when you put them together, represent what we call Moody chart. From Moody chart can help us, if we know 2 of the parameters, to know the third one. Okay, so if you want, Moody chart is equivalent to an equation, but instead of using a numerical equation, they performed an experiment and we have all curves. So or we can use the empirical relation developed, or we can use the Moody chart. Okay, now we will learn here how to use the Moody chart. So as you can see here, you have 3 axes. This axis, this one, represents the axis for factor F, which is the coefficient of losses related to major losses. You have this axis here is for variation of Reynolds number. Okay, so for several Reynolds numbers. And you have the axis here is for different values of epsilon over d. Okay, so if you know 2 of these parameters, you can calculate the third one. Okay, so for example, if I tell you epsilon over d is 0.02, let's say, so you go over the curve of 0.02. So let's say here, this is the curve of, if I follow it, this is the curve of 0.02, like this, and then here it is going upward. So if I give you, for example, if I give you for Reynolds equal to, for example, 10 to the power 6, this is Reynolds 10 to the power 6. I go up, okay? The intersection point, when I reach the intersection point, it will give me the corresponding value of f. So now I will take a new line from the intersection point towards my axis. I can read the corresponding value of f, okay? And I can give you, for example, f and Reynolds, you get epsilon over d. So you have several possibilities. Depending on your the input, you decide on the output, okay? Now, in this problem, what do we have? We don't have two of the parameters. So let us go back to the given to see what is the information we know, okay? So sometimes if you don't know two of the parameters, you should do an assumption to continue. And we'll see how to do this assumption, okay? So first, as we said, we got a relation between F and V by writing what? By just writing the energy equation. So writing the energy equation gave us a relation between F and V. But F is not known and also V is not known. So I have here two unknowns, okay? Let me continue. Now, I will try to know other informations about epsilon over d. How to get epsilon over d? The diameter is given, it's 4 inch, okay? I still need an information about epsilon. To get epsilon, you should look at the type of your pipes. So here, they said you have galvanized iron vent, okay? So you have galvanized iron as material. So you have also a table which will give you the roughness depending on the material of your pipe system, okay? So I will give you the table here. The table is in the book and it's table 8.1. If you look at table 8.1 for different material types of pipes, they give you the corresponding roughness and they give you the roughness in feet and in millimeter. Now here, because we are working in English units, so we will take the value in feet. So for galvanized iron, the case is epsilon of 0.0005. Okay, so I know now epsilon and the diameter is given, so I can calculate in my problem what is epsilon over d. So at least I know the first parameter, okay? Epsilon over d is equal to 0.0005 over the diameter is, I think it's given as, let me check. So 4 inch, okay? So don't forget, as we said, to convert to feet, okay, which is 4 over 12. So if you do the ratio, you can get the value of epsilon over d, okay? So we can see it here. So epsilon over d is 0.005 over 4 over 12, which will give us a value of 0.0050. So this parameter is known, but f, so the first parameter is okay for me, I know it. Epsilon over d is 0.0015. F, I don't know it. Let me check now if I can find the Reynolds number. The Reynolds number by definition, okay, is if I have a circular pipe, a circular duct, the characteristic length will be d, the diameter, okay? So Reynolds is, you are familiar with the formula rho vd over mu, rho v d over mu, but rho over mu, you can replace it by the kinematic viscosity. So this is the kinematic viscosity here, okay? And here, if you have, since you have water, you should look at the kinematic. So from, because they gave us the temperature, from the table in the book, we can get mu, okay, the characteristic of water at this temperature. So we get the kinematic viscosity and we replace it in the relation. But V is unknown, okay? So Reynolds will be expressed function of V. So what I can conclude now that Reynolds is unknown, F is unknown, but epsilon over d is known. But what I did is that I wrote two equations. Equation one, I expressed F as a function, okay, function of v, g of velocity. And here I expressed Reynolds as a function of velocity. So I know, okay, I know both F and Reynolds function of v. but I don't know the value of each one. This is why here the Moody chart will be like a third equation, okay? Because here you have three unknowns. What are the three unknowns? F, Reynolds, and velocity. Okay, these are your three unknowns. You have written two equations only, but you know that if I have two equations, I cannot solve. I need a third equation, okay? So the possibility is or to use a third equation. What will be the third equation? The equation of Moody chart. And when they did Moody chart, they did the analysis, they come up with empirical relation, this one, okay? This is an empirical relation relating Reynolds to the friction factor F to epsilon over D. But as you can see, this is a complex relation and it might not be easy to solve numerically. So instead of doing a numerical solution, we can go for using the Moody chart. And the purpose here is to know the method, how to use the Moody chart in this case. Since we don't know two parameters, we only know one parameter, which is epsilon over D equal to 0.0050. When you have two parameters unknown, you should solve by iteration. So you should do an assumption, and then you should verify your assumption. And if your assumption is not verified, you should repeat the calculation. Now, what I will give you in these sessions, I will give you hints to know how to do assumptions. Okay. So first, since you know epsilon over D, let us go to Moody chart. Okay. So if I go to Moody chart, okay, what I know is epsilon. So this is the parameter that is given for me, 0.050. If you look at this figure, you can see that this is the curve in green that I represented for you is the curve corresponding to 0.0050. But as you can see, you have a major part of this curve that is flat. So a good assumption to start with, because you have a nearly flat curve. So this means that in this region, the Reynolds number is not affecting a lot my result. So a good point to start with is to do an assumption for the friction factor equal to 0.022. So this is an assumption, okay? So I start always when I know epsilon over D, the best assumption to do is to take the corresponding friction factor of the flat curve. And for the flat curve here, okay, if you extend the flat curve, you can read a value of friction F equal to 0.022. So this is an initial assumption to start with. Okay, initial assumption. Now, how can I make sure if my assumption is right or if it's far from my real case? Now I will go back to my equation, because together we wrote two equations, one giving F function of V, one giving Reynolds function of V. Okay, so after doing the initial assumption, what can I do? So I replace F in equation 1, which will give me what? Which will give the velocity, because in equation 1 I found F function of V. Okay, so which will give V. And now once I get V, I replace in equation 2, I get what? I get Reynolds number. Okay, so replacing in 2, I get Reynolds. So what should I do now?
دكتور فيك ترجعي تعيدي الفكرة بس بليز هيك in general.
Yeah. Okay. The whole idea here is that when you use the Moody chart, okay, when you use the Moody chart, you need two inputs to find the third one. Okay. So what to do if I have only one input and I want to find the other two? What should I do? The first thing I should do is I should write equations relating my variables. And these equations always are the first equation you can write is the energy equation, always. So the energy equation will give you a first relation. Okay. Now, a second relation will be to write the Reynolds number equation, because Reynolds is rho Vd over mu. So when you write Reynolds, you can relate Reynolds to velocity. Here to velocity, sometimes if velocity is given but diameter is not, so sometimes I get Reynolds function of D. So it depends on the problem. Okay. And Other equations that I can write, for example, is Q constant. So it depends on the problem. Here, when I wrote that Q is constant, I got that V1 is equal to V equal to V2. Okay. Now, here, Q constant is already used for the energy equation. So I am left with two equations, 1 and 2. And equation 1 gave me the friction factor as a function of velocity. Okay. So this is equation 1. And equation 2 gave me Reynolds as a function of velocity. Okay. So what do I know now? I know how F and Reynolds are related to V, but V is unknown. And still, I have three unknowns, two equations. The Moody chart will be like a third equation. Okay, but it's not, if you want an explicit equation to solve numerically, no, it's a graph. And this graph needs two inputs to give me an output. Since I don't have two inputs, I have only one, I should start by doing a certain assumption. How to do this assumption? I go to my graph. I look at my graph. I can see that for the epsilon over d value, I have nearly a flat curve for high Reynolds numbers. Okay, so I can say, because for a high interval of Reynolds numbers, I have nearly a flat curve, I can start with an assumption of a friction factor corresponding to this flat curve. So if you extend your flat curve until here, you can read a value for friction factor of 0.022. Okay, so you can say, as initial assumption, to be able to start my calculation, I will assume this value of F0. Well, of course, this might not be the accurate value, but how you know if it's accurate or not? By iteration. What I mean by iteration, now once you have F, you go to equation 1, what can you get? Since F is function of V, if you replace F0 by its value in equation 1, you get the velocity. So now, when I replace here, I can get V. Okay, I can get V0, which correspond to F0. And then when I replace V by its value in the Reynolds equation, I can get Reynolds number 0. Okay, now what I should do, I should check if V0 and Reynolds 0 will correspond really to F0 or not. How can I do this? I already have epsilon over d, okay? And now I calculated my new Reynolds number, this one. So if now I know two parameters, epsilon over d and Reynolds, so how can I find a new value of F? I can find it from the Moody chart. So here, if you perform your calculation, I will show you how they did it here in the solution. Okay, so as we said, since we have two unknowns, we should do a certain assumption, okay? And the assumption, as we did, is 0.022, and I explained for you why we choose 0.002, okay? So here they are explaining it for you. They are saying that it is usually the simplest to assume a value of F, because the correct value often lies on the relatively flat portion of the Moody chart, for which F is quite insensitive to Reynolds. So always when I have epsilon over d, it's recommended to start with the value of F corresponding to the flat curve. Now, once I know the value of F, I replace in first equation, which will give me the corresponding value of V. Then I replace V in the second equation, which will give me the corresponding Reynolds. So now I get a new Reynolds. Reynolds, I don't have it. So this is a first assumption for Reynolds, 21.2. Okay. So now what I should do, I should go to my Moody chart and put Reynolds equal to 21.2 times 10 to the power 3, which is, if you want, it's 2.12. This is 2.12 to the power 4. Okay, so now I will go to my Moody chart and I will replace Reynolds by the value I got here from my iteration. Okay, so here 2.12 times 10 to the power 4 is nearly here. So here you have a logarithmic scale. Okay, so just, and you have lines, you can follow lines. So nearly 2, this is 2 times 10 minus 10 power 4. So you go little bit, you little bit one division nearly, okay, or less than one division, because each division is let's say we are having 5 divisions, so each division is 0.2. So nearly 2.12 is corresponding to the blue curve, okay? So I considered a blue vertical line. The blue vertical line will cross the line of epsilon over d, which is the green line at this point here. So here you look at the intersection point between the green line representing epsilon over d curve and the blue line corresponding to a Reynolds of 2.12. And then if you read the corresponding value of friction, it's nearly 0.029. So as you can see, there is a large difference between your initial assumption and F1. So you cannot stop here. You only stop when the two last values of F are very close. Okay? So for example, if you obtain 0.023, then you can say my assumption is fine. And if you have a difference less than 10%, you can stop. You can say, I can stop my iterations. Here we cannot stop because the difference is 7 over 22, which is large. So it's nearly 30%. Okay? So I cannot accept such difference. I should repeat everything. I should, again, calculate a new velocity, calculate a new Reynolds number, and plug in again in the Moody chart. So now, if I go back to my equations, I replace F by 0.029. I will get a new velocity V1, and I will get a new Reynolds number 1 now. Okay, so let us see what was the result of calculation. What was the new Reynolds number? So when they plugged here in the relation, they obtained a new value for Reynolds, okay, which is equal to, let me check here. Yes, here it is. So now it's 21.2. Okay, sorry, 20.5. So first it was 21.2 times 10 to the power 3. Now it's 20.5 times 10 to the power 3, or the new value of Reynolds is 2.05, which is very close to the previous one. Okay, so previously I obtained 2.12, now I obtained 2.05. So here the difference is small. So I can expect that F will be close. Okay, so to the power 4. So what I should do now, I will go back to my Moody chart to verify that F is very close to the previous value. So here, if you take the line for 2.05, it's the line here, okay? So as you can see, the two lines are very close to each other. So here you have that this line, the second line, corresponds to 2.05 times 10 to the power 4. If you take this line, its intersection with the green line is nearly the same point. Because the new value is very close to the earlier one, the intersection point is nearly at the same location. So F1 and F2 are nearly equal to 0.029. So you can say that I can stop now because the second iteration gave me nearly the same value of the previous iteration. So my friction factor is 0.029. My Reynolds number is 2.05 times 10 to the power 4. And now, once I have my friction factor, I can get my velocity because Reynolds is given and F is given, so I get V. And now I can just replace in my energy equation, okay, to calculate my unknown. Okay, so I am nearly done. So what was the question? Now I can go back to the question. Okay, so maybe the meeting will end. I will open a new session, okay? So let me open a new session to continue the